Please join me in welcoming the second finalist for today, Vattenfall.
Thanks. It is a great honor to be here today, representing some work which is significant for all our business. And of course, it's a huge honor for us to also be part of the finalists for the Franz Edelman Award. It will be big for the team, but it will of course also be very big for us as a company and what we are looking at. I'm Michael Simmelsgaard. I'm heading the offshore business within Vattenfall. Some of you might ask a simple question. Who is Vattenfall? I know you had IBM on before, and even in Europe we would know who those are. But if we look at it, then we are one of the biggest utilities in Europe. We are approximately 20,000 employees. And what we are known for is actually leading the energy transition in Europe. So what I'm going to present today is the work which is a combination of 4 years of collaboration with Bologna, with the Technology University of Denmark, and Vattenfall. What I would like to tell you about is what does it mean for us? We are a simple company. We work for fossil-free within a generation. Fossil-free within a generation means that we are able to keep what we promised in the Paris Treaty, keeping the global warming below the 2%, 2 degrees, sorry. 2 degrees is a huge difference to the world climate. I represent a Scandinavian company. And of course, in a Scandinavian company, it's very easy to argue like that. What we have achieved over the last 3-4 years is making renewable fully competitive with how a coal plant produces power. That's what this project is all about. I will go into details a bit here on what does it mean with fossil-free living for us as a company.
Our world urgently needs to change and find alternative ways for cleaner powering and heating. Change has to happen, and fast. At Vattenfall, we believe the solution is energy that is free from fossil fuels. We need to change how we live, how we work, how we produce, how we build, how we travel. At Vattenfall, we're determined to power and lead this change. We exist to help all our customers live their lives in ever climate smarter ways and enjoy fossil fuel-free lives within 1 generation. As one of Europe's leading energy companies, our ambition is to become fossil-free ourselves. But that's not enough. We also actively seek new partnerships inside and outside the energy industry, searching for new ways to achieve fossil freedom. For instance, we collaborate with the steel industry to develop a method for producing fossil-free steel that emits water instead of carbon dioxide. We help our customers to adopt smart technologies to create their own electricity or heat in an easy and affordable way. We are building a network of charging stations in Northern Europe, together with our partners, to accelerate the transition to electric cars. Our journey to fossil freedom is actively underway.
What does offshore play in this whole game? We take approximately 2/3 of our investment budget every year to invest in wind. And that is basically the key enabler for actually getting into fossil-free freedom. But it's a strong competitive market. If we look at the competition we see in Europe, we see it going into US, we see projects in Taiwan. It's a heavy competitive market. We look at Block Island that gave very high subsidies. If those were the benchmarks of the industry, we would actually never see a transition to renewable energy. So what we have been doing, and that's what we've been using our operational research for, is we have used 6 gigawatt of projects where we have estimated what kind of benefits can we achieve out of that. We have achieved $170 million in really savings as to the given projects where we are today. And of course, what I would like to give you a short introduction to what it is before I hand over and give the details of the operational research that has gone into the project.
The establishment of wind energy farms in Europe is based on an auction system. When planning their energy infrastructure, each country constructs energy capacity according to the expected demand, with some energy capacity being assigned to wind farms. To have these farms built, the government typically offers an area for tender. The company that can build a farm that requires the lowest subsidy will win both the tender and the right to construct and operate the farm. That means that only the company with the lowest bid can capitalise on their investment and sell energy in that country for the lifetime of the farm. That means it's essential for companies like Vattenfall to be realistic in these bids and find innovative ways to win the bid while still making a profit. Vattenfall uses operations research to be more competitive in the offshore business, focusing on 2 key aspects of the wind farm design process: turbine allocation and cable routing. When Vattenfall enters a tender, there is a specific area where turbines can be placed. Based on the demand and on the internal grid capacity, the state also fixes the capacity of the farm. The capacity of a farm is the maximum production that a specific farm can possibly produce. Once the experts in Vattenfall decide which turbine model to use, the limitation translates to a maximum number of turbines that can be located on the site. The optimiser must decide where to exactly place turbines in the available area so that the best profit is achieved. This means maximising revenues, such as power production, and minimising position-related costs. But how can a higher production be achieved while reducing costs? The key is to consider the variability of the wind in the site and the so-called wake effect. If we can place the same turbines in a different way, so that they cast less shadows on each other, we can achieve higher production without changing our costs. Old farms had a very regular structure, with turbines on a regular grid at a fixed distance to one another. Our operations research tools show that these layouts are not optimal and highly affected by the wake effect. As the wind varies greatly over the lifetime of the farm, the optimiser needs to consider the full variability of the wind when deciding the turbine location and computing the revenue losses due to wake effect. So the challenge is to decide the location of turbines, considering not only the wake effect from one direction, but considering all possible wind scenarios with their frequencies. In practical applications, we consider hundreds of thousands of possible wind scenarios for each optimisation. And we do even more than increase production. We can also look at reducing costs at the same time. The optimiser can indeed also consider position-specific costs that were never considered in the layout tools previously used by the company. Depending on the water depth and on the soil conditions, different foundations may be needed across the site. Building a turbine in some positions may therefore be more expensive than in others. The optimiser can consider this explicitly and balance out higher production against higher costs. We also considered the challenge of optimally connecting all turbines with electrical cables. Different cables with different costs and capacities can be used. We used operations research to design the optimal cable route between the turbines in order to minimise costs. The overall impact of using operations research and analytics in the design of offshore wind farms compared to the old methods to solve the challenge has been estimated to be worth around 10 to 15 million euro for each wind farm. The optimisers also opened the road for digitalisation and more data-driven decisions in the evolution of Vattenfall's wind farms.
To talk more about the project, I invite Martina Fisquera, who has been leading the development of the project, to the stage.
Thank you very much for the introduction. So I will cover the more technical part of the project, and in particular I will start with the layout optimization part of the project that consists in deciding where to locate the turbines in a given area. So in this picture you can see an old park owned by Vattenfall actually, and what you can notice is that the turbines are located in a very regular way, on a regular grid. And this was the common wisdom some time ago when the process was handled using different techniques. Today we know that these kind of layouts are highly suboptimal, mainly due to the wake effect. The wake effect is the interference phenomenon you can see in this picture. So this is exactly the same park as I've shown you before, and in a specific wind condition, where you can see that the first turbines are heated by full wind, and all the others are in the shadow of the first ones. So the result is that all the turbines in the shadow cannot produce as much as if they were out of the shadow. So it's extremely important when we optimize the layout of a site to consider this wake effect. So to be more specific, when we enter a tender, Vattenfall is given a specific area. There is also a maximum capacity of this area, so a maximum production that this farm can produce, and this translates in the maximum number of turbines that we can place in the site. So the optimization question is how to locate these turbines in order to maximize Vattenfall profits. So the main part of the profit is related with revenues. So how can we locate turbines so that the overall farm can produce more? So reducing this wake effect I talked about. But another key point of this is also reducing our costs. Because in specific sites, in complex sites, we have that the soil condition may be very different in the area, and also the water depth may be very different in the area. So the result is that we need specific foundation types for each possible position, meaning that some position may be more expensive than other positions. For the first time, we have been able to consider this in the optimization using operation research so that our tools can balance between a possible higher revenue because of higher production and possible higher costs for position-related costs. So we quickly realized that this problem is a location problem that can be formalized in a mathematical way. So what we did is we take all the available area and we discretize in a number of possible positions. For each position, we have a binary variable that represents if we locate a turbine in that position or not. So we realized that we can formalize the problem as a mathematical model. And to answer the needs of the company, we developed an original mathematical model that captures all I've told you before in the previous slides. What is very interesting from this model, compared with the model existing in the literature, is that we could solve bigger instances. So models from the literature can solve until 100 possible positions, while this model can solve until 1,000 possible positions. Another interesting point of this model is that we can easily consider the stochasticity, so having a stochastic programming variant of the previous model. Indeed, we now know that it's very important to consider the variability of the wind. In common wisdom, so with old parks, we were mainly focusing on the main direction of the wind. So when we locate turbines on a regular grid, normally we space more the turbines on the main direction. But now, thanks to operation research, we can actually consider the full complexity of this, and we understood that it's not enough to consider only one wind direction, because in that case, we risk the wake effect we have in this picture, for example. So it's very important to consider the full variability of the wind, and in practical application, we receive hundreds of thousands of possible wind scenarios for each optimization. So this is a big advantage of the model we developed. But when we went to reality, so when we asked the company, okay, let's start to do it for real, we realized that reality was more complex than what we were studying in the research part of the project. Indeed, we were given instances of more than 20,000 possible positions. So we realized that the model we developed wasn't enough, and we had to look for innovative solutions to solve these way more complex problems. And what we did is that we used a new framework developed in the operation research literature called math heuristic, where the main idea is to mix the strengths of the mathematical modeling, math, and the strengths of the heuristics approach, heuristic. So just to give you an overview, what we do is that we have a kind of an heuristic where we look in the neighborhood of the best solution we have so far, using the MyLP solver as a black box. So this innovative solution was actually very good in practice. So it's interesting from a research perspective because we compared our method with the other possible methods to solve the same problem. What we noticed, so here you can see two graphs related with two instances. The first one is with 5,000 possible positions, and the other one is an instance of 10,000 possible positions, so big instances. And we compared our method, here indicated with the black line, with possible competitor methods that are purely heuristic methods, the blue line, and red and green that represent purely exact methods with different settings in the MyLP solver. So in the plot, you can see on the x-axis you have time versus on the y-axis the profits. So the higher, the better. And what you can notice is that our strategy, represented in black, is able to outperform all the other methods, and it can find very good solution very quickly. So this has been very interesting from a research perspective, a very challenging optimization problem, but is also very interesting in practice. So to let you understand what is the impact in practice of using these techniques, I'll show you a real example where we did the validation of this software. So this is a real-world site, and in green you can see the available area. So we can locate turbine wherever in the green zone. In this specific site, the soil conditions were also complex, so we had to consider also the different costs related with different foundation types across the site. So to do that, we have a cost map that represents in red the more expensive position and in blue the less expensive position. So in this slide, I'm not showing the numbers for privacy reasons, but the idea is that we want to balance between having higher revenue, selling the energy, so having higher production, and also the costs relating with installing the turbines and their specific foundation types. So to understand what was the impact of using our technique, we compare it with the classical method that was used in Vattenfall to solve this problem. So the classical method in Vattenfall was to use some commercial software existing on the market. The problem with this commercial software is that they cannot consider explicitly the cost part, but they are only maximizing the power production. So what they were doing was to optimize based on power production and then manually move the turbines that were in the most expensive position. So the result is indicated in pink, the pink dots in this plot, while our result using operation research is in black. We give these two layouts to a third team that is an expert in forecasting and simulation, and ask them what is the difference here. And they estimate that our layout is able to increase the revenues of Vattenfall for about $14.2 million for this specific site. It's interesting to see that our optimization is more powerful than the commercial software also when we compare Apple with apples. So if we try to optimize only on power production, we still see big increase in revenue, so big profits from Vattenfall side compared to the classical methods, so the commercial software. This site I'm showing here is actually a very important site for us. It's called Holland Kust Zuid, and it's going to be the first site to be built subsidy-free. And this is a site that Vattenfall won in the last years. So again, we compared our result with the result using the classical methods, and in this specific site, the savings were about $11.5 million. Another point that we considered in our project is the optimization of the cable routing. So once we have the turbines in the site, we need to transfer the energy from the turbines that are offshore to shore. To do that, the classical method is to connect all the turbines to a connection point called offshore substation that you can see in this picture. Then from the offshore substation, there is a huge cable called export cable that moves the energy from there to shore and to the grid. So Vattenfall business focuses on the connection between the turbines and the offshore substation. So in this problem, we are given the positions of the turbines and the position of the substation or substations, and it's our goal to connect all the turbines to the substations, minimizing the costs. So also here we realize that this is a problem on a graph where our turbines are the nodes of this graph and the substation is the root of this anti-arborescence. And so we developed an original mathematical model that could capture all the needs from the company. We have our variables on the arcs of this graph, and our goal is to decide how to connect the turbines to the substation, minimizing the costs. An interesting point is that we also have an available set of cables that we can use. So it's not only the question of which turbine to connect with which turbine, but also what kind of cable to use. And different cables are characterized by different costs, different capacity, and then different electrical characteristics. I'm showing here another feasible route for another case so that we can go through the constraints of this problem. So the black dots represent the turbines and the red square is the substation. All the turbines are connected to the substation using different kind of cables represented by different colors. We fulfill the capacity, so every type of cable has a given capacity and the current that passes through that cable must not exceed this capacity. We are also asked to avoid cable crossings, that is a bit challenging from an optimization perspective, and we are also asked to avoid obstacles. So in this specific example, the black areas are obstacles, so area we cannot pass through. Also, the substation has some limitation that translates in a maximum number of cables that can be connected to the substation. And another interesting point we consider is cable losses. So when we talk about minimizing costs, we can look at the immediate costs, so the cost of the cables and installation, but we can also look at cost over the lifetime of the park. Indeed, when the current passes through the cable, part of it gets lost due to the resistance of the cable. And this is, of course, a lost revenue for Vattenfall. So what happens in practice is that more expensive cable has also lower resistances. So the question is, should we invest in more expensive cable to actually reduce these losses over the lifetime of the park? And for the first time, we have been able to answer this question using operation research by including these revenue losses in our optimization. So again, first step was to develop an original MILP formulation for this problem because there was no model on the literature that was capturing the full complexity of the problem as it was in practice. Another main advantage of developing these kind of tools in the company is that we are very close to the practitioners and we can answer to their needs. So in particular, we develop different variants of this model I just explained to you, depending on their specific need. So here I'm showing you 3 examples on a real-world case located in Denmark, the Vattenfall site, of course. So on the first plot, you can see what happens if we let the optimizer free to use to define the structure of the cable. So if we use the model as I explained it to you so far. Some kind of turbines actually have some extra cost if you want to connect more cable to them because you need extra hardware. So what we did is that we modeled this in our optimization, so this kind of cost that is not linear with the number of cables that connects. And we obtained the second version of the tool that you see in the second plot. And finally, we have another version where we force a structure that I call the loop structure. So this is a structure that you use to be more safe for failures. So we are required to connect all the turbines in string, so only one cable entering and exiting each turbine, and to connect each string to each other with a redundancy cable, so to be safe in case of failures. So our tool can have all these structures encoded, so we can run it with this different option, with the advantage that the user can practically compare them and quantitatively, for the first time, see what is the impact of using one structure over the other one and take more informed decisions. Also in this case, when we use this model in practice, we realized that the reality was more complex than what we expected. And in some specific sites that have a lot of turbines or very strict limitation may be very challenging. And the MILP solver sometimes cannot neither find a feasible solution. So what we did is, again, to use the same idea of before, so this math heuristic framework, where here the idea is that we try to heuristically decompose solves our problem. So we generate a first feasible solution, also disconnected is fine. Then we fix some marks in the solution, and we optimize using the MyLP solver on the remaining arc. And we iterate until we get a good solution. With this good solution, we warm start the MyLP solver, hoping to get to the proven optimal solution, or at least having an understanding of the quality of the solution we give to the practitioners. Again, also this project was very interesting in practice. So to show you this, I'm comparing our operation research results with the results using the standard methods in Vattenfall. So this is very interesting because this problem was tackled manually inside the company. So a manual operator and expert was given the position of the turbines, the black dots, a set of possible cables to use that here are represented with different colors. So the black is the cheapest one, but also has lower capacity. The green is intermediate, and the blue is the most expensive, but also the one with the highest capacity. So this is the result from the expert in Vattenfall. As you can see, it's a very nice and regular layout. What we did afterwards is to give the exact same data to our operation research tool. And this is the result we got. So as you can see, it's very different from the manual one. You can say it's maybe less pretty and regular, but you can also see that it's $1.7 million less expensive than the other ones, just by doing things in a smarter way. As I said, we can also consider power losses along the cables. So we did this for the specific site. So in this that you have seen, we optimize only based on the immediate cost of the cables and installation, while in this other layout, we also consider the power losses in the optimization. So you can see that the result is slightly different from the previous one and is very different from the manual one still. And what you can see is that this layout is still $1.7 million less expensive at construction time compared with the manual one, and is also $1.9 million cheaper in 25 years. So now that I give you an overview of what the problem is and the techniques we have used to solve it, I would like to show you a little testimonial, some testimonials, where you can see how the project developed and what is the feedback from the people that use the software and that use the results from the software.
I'm Thomas Hjort. I'm heading the system design department in Vattenfall's offshore wind division. I had the pleasure 3 years back of encountering a master student in mathematics, working on something as strange as operational research, something I didn't know anything about. And when I saw it applied after the master student project, when I saw it applied to the wind farm layout as a whole, it really became an interesting journey to be part of. We decided to create a small department that works on modeling an entire wind farm and thereby be able to explore different ways of designing the farm in very short time and with high benefit for our business cases.
In system design, we design the wind farms of the future. Basically, we start with an area of sea, and through the model framework that we've created, we are able to make a design of the wind farm and a corresponding business case. The optimizers that optimize the wind farm layout and the cable routing are an essential part of this because they affect basically all aspects of the business case. The results that we produce are then used by management for decision making and to drive the design of the offshore wind farm in the most promising direction. Basically, in short, it gives us a better business case in a shorter amount of time. So previously it would take many weeks and a lot of manual work to make a first design for an offshore wind farm. And basically, because it took so much time, we could only consider very few options. Now, with the model framework, of which the optimizers are a key element, we have been able to reduce the many weeks into just a few hours. And that enables us to run many more different options. And from those options, we are able to then select the best business case possible.
I work at Vattenfall as an electrical package manager, and today I'm one of the final users of the results from the optimizer. My work focuses on the practical implementation of the optimal design received from our system design team, and I could say that I'm quite impressed from the results received from it. Delivering high-quality solutions in a very effective way is reducing dramatically the human factor error and is also helping us to cut down the post-processing time. Before the introduction of the tool, as an example, we were doing the design of the cable connection between turbines ourselves, purely based on our experience. What impressed me the most at the tool is the capacity of considering the entire complexity of the problem at once.
The optimizers are now fully integrated in our way of working, so we basically use it for all the wind farms that we design. For me personally, it is really cool to be able to work with these state-of-the-art models, because I know it gives me the best tools to design the most competitive offshore wind farm. It's also tools like these that I know then that give me the edge over my competitors. And for the industry as a whole, it's of course very important, these innovations that drive down the cost, because that is what will enable offshore wind energy to be a key part of a greener energy system. The optimizers and the model framework in general basically triggered a new way of working in Vattenfall, because it allows us to quantify many different options that we consider for the offshore wind farms. And because of that, we don't only can rely on experience, but we can actually put numbers to all the different options that we want to consider.
D2 was very happy about the collaboration with Vattenfall, and I'm personally very proud to see how much the results are being used in practice and how big impact it has had in the company. When we started the research project almost 4 years ago, we very quickly realized that it's a very complex problem with many contradicting constraints that are difficult to combine, and we had to invent new, innovative ways of solving the problem, combining operations research techniques with artificial intelligence and many other techniques, pushing the limits for what can be obtained.
So of course we are happy. A direct impact of $170 million for a company our size, that's a lot of money. We have had, and on top of that, we have been successful in the 3 out of the 5 most competitive auctions that has been across the world, and we have basically taken more than half, which is a little bit more than the hit rate we have been used to. We have also been asked very clearly by both our investors and very prominently by Bloomberg that says, are you crazy with that kind of bid level? Is it really savings? Can you really deliver what we're looking at? We got that for Horns Rev, we got that for Kriegers Flak, for Hollandse Kust. Even our competitors started saying, this is not wise. But to give you a little bit of trust that what we have done actually has a sustainable long-term operational effect is we have taken FIDs. We are going to inaugurate the first one, the Horns Rev 3, in about a month's time from now. We have taken final investment decisions for the Kriegers Flak. And just this morning we announced for Hollandse Kust that we have placed a close to $1.5 billion purchase order for turbines for the Hollandse Kust projects, which I can tell you, there's a lot of GE people that might be a little bit dissatisfied that it wasn't them, but on the other hand, that really is a strong commitment to the fact that we will be successful in building the world's first subsidy-free wind farm. And that is basically based on what we have done here. If we then look at it, what has it done to the company? I think the testimonial said it very clear. We moved away from a very manual process where we could consider 1, maybe 5 layouts throughout the process. When we got the Danish new auctions announced, within 3 days, I had the first decision proposal for a bid level on my table. That would normally take 3 months for somebody to say, this might be what you're looking at. Now I'm confident that what I'm looking at is actually incredibly close to what we are doing. So due to the objectivity of how we actually work with operational research, this gives us a lot of that confidence in our decision making. But it's of course a complete new way of working. So we have had a lot of people looking at Martina with the very objective saying, yeah, you don't really know it's big things, it's foundations. They are heavy. They weigh 150 tons. So it's really huge components. And you still, with the objectivity, could at least convince, as you could see, how we actually develop. Hollandse Kust was up before. It is a milestone project in the industry. This is where we basically have proven that it will be subsidy-free. This is why, no matter your opinion in any country about whether renewable energy is the right or the wrong thing, as long as you're subsidy-free, meaning competing directly against gas, coal, this is a proof point that the whole industry works. So that's a fantastic proof point, what sustainable improvement across the whole value chain. We now use it for discussion with our supply chain on how we actually bring developments further. So the turbines we announced this morning here, we are the absolute first one, and we actually simulated that already 1.5 years ago, that this would be the right turbine for the given site. To give you a little bit of the appreciation we also see across our company, I've asked my CEO and my CFO to at least give you some kind of indication of what it means for us as a full company.
Hi, I'm Magnus Hall, President and CEO of Vattenfall. I'm very proud that our efforts in using operations, research and analytics in the wind business have been recognized by our presence as finalists at the Edelman Award.
My name is Anna Borg and I'm the Chief Financial Officer of Vattenfall. I'm happy to share with you my opinion on this wind farm design optimization tool that has been developed internally in Vattenfall. We are constantly growing and adding more wind into our portfolio. Out of our total investment budget between 2019 and 2020 of approximately $6 billion, more than $2.5 billion are going into wind.
Digitalization is leading to changes across the entire value chain for the whole energy industry. In operations, the trend, among other things, is to cut costs through automation and optimization tools, which is exactly what the wind farm design optimization software developed in Vattenfall's wind business delivers. These data-driven optimizations tool has had a huge impact on our way of thinking about the wind farm design process, and they allow us to take more informed decisions, which also leads to much better business cases.
But the competition is increasing as well, so it's important for us to make sure that we constantly find new and innovative ways of improving. This wind farm optimization tool is increasing the profitability and decreasing the cost, so the impact can be as much as $10 million per wind farm. This means that we can become more competitive in the auctions for winning the possibility to actually build these wind farms. But it also means that we can be more profitable once we are up and running with the wind farms.
The optimization software is now fully deployed, and all our offshore wind farms are designed using these tools. Thanks to them, we can achieve better layouts in significantly less time, which allows us to experiment with more options and take more informed decisions. This kind of innovative solutions are of key importance for Vattenfall's wind business to be successful, but also to deliver on our purpose to enable fossil-free living within one generation.
As a summary of that, it is great to work in a company that has fossil-free being the main objective of what you do, because that really is a strong impact on the human life. On the other hand, working and saving $170 million is actually, as a businessman, also quite an achievement. We established the team simply to continue working on the optimizations so that we can be faster in all our developments in how the wind farms develop over time. So by that, we will make sure that we stay ahead of competition, because a competing industry which has a strong purpose drives a lot of people's focus. So we clearly need to balance building wind farms. And if you have any idea how many wind farms we need, then in Europe alone, to meet the Paris Agreement, it's 100 to 150 wind farms that needs to be built in the next 10 to 12 years to cope with the climate change. So with that being said, I'm really honored to be here presenting this project today because it makes great sense for the company, great collaboration with the institutions, and it has really been adapted and received well in our organization. With that, thanks for your attention.